Okay, what we're going to do today is we're going to talk about, or we'll continue solving oblique triangles. And today's lesson may be split up into a couple of parts. I don't know if we're going to have time to actually get through everything, but I'm actually going to bring up the formula sheet, right? I'm going to bring up this all exam formula sheet. And on the first page at the very bottom, the last time we met, we talked about the law of sines. And we also talked about the four cases, the data that are required to use the law of sines. Today, we're going to talk about the law of cosines. And I'm going to make some adjustments to the formulas because these formulas, they actually fit a triangle that has a standard labeling of A, B, and C as the angle measures, and they also have the standard labeling for the side lengths as lowercase a, b, and c. As far as x, y, z is concerned, they're using, instead of using angles capital A, capital B, and capital C, they're actually using the Greek letters of the alphabet, alpha, beta, and gamma. All right. Another thing I'm going to keep in note that the formulas that we actually see here, these aren't the actual formulas that we're going to use. Like, for example, if we were finding the length of a side of a triangle, okay, we would actually find A and not A squared, right? So in order to solve this for A, we would take the square root of both sides. And also, if we were to find an angle measure, right, we'd have to take these formulas and we would have to algebraically solve them for an angle measure. And I'll kind of explain that momentarily. We're also going to take a look at um, Heron's formula. And using Heron's formula, it's actually the formula to find the area of a triangle if you're given all three sides. In the last class, we looked at how to find the area of a triangle if you were given a side angle side set of measurements. Okay, we were able to use these particular formulas. Today, we're going to take a look at how to use Heron's formula to find area. And you would use Heron formula when you're given only three side lengths. All right, so that's where we're headed. I'm going to pull up OneNote, and I'm also going to flip my screen around. All right, and we're going to take a look at the law of cosines. Okay, now as far as the triangles that we're going to deal with in this course, all right, so this is basically would be the standard labeling. Okay, that's used in the XYZ course. So we're going to have angle alpha, we're going to have angle beta, and we're also going to have angle gamma. All right, so instead of using capital A, capital B, and capital C as are in the formulas, we're actually going to use alpha, beta, and lambda. The side that's opposite angle alpha is side A. The side opposite angle beta is side B. And the angle opposite, the side opposite angle gamma is side length C. All right. So now here are the actual formulas. All right. So the first formula we have is A squared is equal to B squared plus C squared minus 2BC times the cosine of alpha. The second formula is B squared is equal to a squared plus c squared minus 2ac times the cosine of beta. And the form c squared is equal to a squared plus b squared minus 2bc times the cosine of gamma. Okay. Now for each one of these setups, we'll take this first one, right, where we have a squared is equal to b squared plus c squared minus 2bc times the cosine of alpha. We're actually given a side, right? We're given a side, and an angle set of measurements. All right, so we talked about those cases in the last instance. Now we can't actually set up a law of sines function because we'd have too many unknowns if we were to set up a law of sines trig function. But we could set up a law of cosines. So the data required in order to set up a law of cosines is a side, angle, side set of measurements. Right? If we were to look at, let's say, the first formula, right? If we were to find side length A, right, we would be given side length B, we will be given side length C, and we would also be given, I guess I should write it this way. We'll be given side length B, we'll be given side length C, and we'll also be given the angle included between the two side lengths. All right. If we look at the second formula, b squared is equal to a squared plus c squared minus 2ac times cosine of b, excuse me, the cosine of beta. And I'm erasing everything here. So notice we be given side length A, we will be given side length C, we'd also be given angle beta. All right, and we could find the side opposite angle beta. And the same thing is true for our last formula. Right, c squared is equal to a squared plus b squared minus 2bc times the cosine of gamma. So here again, we will be given side length A, we will be given side length B, we would also be given angle gamma. All right, and we could find the side opposite that given angle measure. All right, so all of these are based on a side, angle, side set of measurements. Okay. So now, as I alluded to, we never really find a squared, we always find a. We never find b squared, we always find b. And we never find c squared, we always find c. So I'm going to take the very first formula, right? A squared, just put these in a box, is equal to b squared plus c squared minus 2bc times the cosine of alpha. And if I wanted to find a, I would simply take the square root of both sides, right? So if I take the square root of the left-hand side, the square root and the square are going to cancel, so out pops a. And if I take the square root of the right-hand side, I have the square root of b squared plus c squared minus 2bc times the cosine of alpha. All right, and this is the formula I would put into my calculator. Right. I could also take this formula and I could solve it for angle alpha. All right, so here I solve for A. Here I'm going to solve for alpha. Okay, so I'll actually derive the first formula, but I'll just write out the other formulas. All right, so I'm going to go back to this original formula. A squared is equal to b squared plus c squared minus 2bc times the cosine of alpha. And I want to solve it for alpha, so I'm going to move b squared and c squared. I'm going to subtract those from both sides. So I have a squared minus b squared minus c squared is equal to negative 2bc times the cosine of alpha. Right, so I transpose b squared and c squared to both sides. The next thing I'm going to do is divide both sides by negative 2bc. So I have a squared minus b squared minus c squared divided by negative 2bc. That's equal to the cosine of alpha. All right. And I'm just going to flip it around before I do anything else. So I'm going to just write this out as the cosine of alpha is equal to a squared minus b squared minus c squared divided by negative 2bc. All right, so the only thing I did here was I just reversed the formula. Now, if I take a look at the right-hand side, I want my denominator to be positive, right? So if you remember your rules from sines, so if I look at my a squared term in the top, it's positive, the denominator is negative, so a positive divided by a negative is a negative. If I look at my b squared term, I have negative b squared. And if that's divided by negative 2bc, a negative divided by a negative is a positive. And the same thing is going to happen for the c squared term, right? Negative c squared divided by negative 2bc would actually equal a positive c squared divided by 2bc. Okay, so I'm going to write it out as such. So the cosine of alpha is equal to b squared plus c squared minus a squared over 2bc. Right, so in essence, I have the exact same thing, right? The only difference is my denominator is now positive. From this point, I'm going to take the arc cosine for both sides, right? So once I take the arc cosine for the cosine of alpha, out pops alpha. I'm going to take the arc cosine of the right-hand side, so that leaves me with the arc cosine of b squared plus c squared minus a squared over 2bc. And this is our second formula. All right, so I'm going to write all of the formulas out. So I'm going to go down a little bit. All right, so here are all of the formulas in their glory. So A is equal to the square root of b squared plus c squared minus 2bc times the cosine of alpha. B is equal to the square root of a squared plus c squared minus 2ac times the cosine of beta. C is equal to the square root of a squared plus b squared minus 2bc times the cosine of gamma. Alpha is equal to the arc cosine of b squared plus c squared minus a squared over 2bc. Beta is equal to the arc cosine of a squared plus, let me spread these out just a little bit. Beta is equal to the arc cosine of a squared plus c squared minus b squared over 2ac. Gamma is equal to the arc cosine of a squared plus b squared minus c squared over 2ab. All right, so I'll just give you a second to write down all of the formulas. All right, so in general, when you see the law of cosines formula, you always only see three. Those are those main three with a squared, b squared, and c squared. But from those three main formulas, you can derive these six formulas. All right, so we'll be referring back to this as we work through some of the examples. At this time, I'm going to go back to Blackboard, and I want to go into lecture notes. And I want to go into section 10.2. And keep in mind, there is a law of cosines video. All right, so here again, here are the formulas for the law of cosines. So just keep in mind, whenever you see the law of cosines, you're mainly only going to see these main three formulas. I'm going to scroll down and take a look at the summary of cases with suggested procedures. Now, as far as XYZ is concerned, they will pretty much ask you what they want you to find. All right. But there may be some instances in which you may be asked to solve to solve an oblique triangle. So here are some of the suggested procedures. Now, they're not so much used for our course because they tell you what they want you to find. But just to be thorough, I must go through these suggested procedures. All right, so in the last class, we talked about the cases. Okay, I'm gonna blow this up slightly. So here again, if we look at the chart, we have two columns. On the first column, we have the oblique triangle with the cases, and on the second column, we have the suggested procedure for solving. So case one says if you have side angle angle or angle side angle, the suggested procedure for solving is you must first find the remaining angle using that sum formula, and then you can find the remaining sides using the law of sines, right, which we saw in the last lesson. Case two is where you have to be careful. If you're given a side angle set of measurements, this is called the ambiguous case. It's called an ambiguous case because you can have more than one solution. You can either have a no triangle solution, you can have a one triangle solution, or a two triangle solution. Now, as far as XYZ is concerned, they don't really go out to the two triangle solutions. All right, but I will go through all the cases and all of their glory. All right. So if you're given a side angle set of measurements, the first thing you should do is find an angle using the law of sines. The second thing you should do is find the remaining angle using the sum formula. And the third thing you can do is find the remaining side using the law of sines. If you have a two triangle solution, you would just repeat steps 2 and 3. Okay, so I'll explain that. May not be today, but I'll kind of explain that side angle set of measurements. Now, I've looked through the homework and there are only 2 problems. I believe there are problems number 10 and problems number 11 that give you a side angle set of measurements. All right, so that's what you should do. The suggested procedure for solving an oblique triangle where you're given a side angle set of measurements. All right, so now here's where we come to the use of the law of cosines. All right, case number 3 says if you're given a side set of measurements, the first thing you should do is find the third side using the law of cosines. The second thing you should do is find the smaller of the 2 remaining angles first by using the law of sines. So we talked about earlier that some triangle facts. The largest angle is opposite the largest side and the smallest angle is opposite the smaller side. So after you find the third side using the law of cosines, you should then find the smaller of the 2 angles using the law of sines. And then the third thing you should do is find the remaining angle using the angle sum formula. If you're given a side set of measurements, you should find the largest angle first using the law of cosines. Now, in our problems in X, Y, Z, they'll ask you what they want you to find first and what they want you to find last. However, if you're not given any guidance on what to find, you should find the largest angle first. Then the second step says find either remaining angles using the law of sines. And then the third step says find the remaining angle by using that sum formula. So I'd be kind of remiss if I didn't go through this. In the previous course, you had to solve an oblique triangle. And to solve an oblique triangle means that you have to find all of the angle measures and all of the side lengths. However, in this XYZ course, we're given information about an oblique triangle, but we're only asked to find one thing. Like we only asked to find a side length, or you're only asked to find an angle measure. You're not required to solve the entire oblique triangle. All right. So I wanted to go through the suggested procedures just in case you come across an example or you're trying to solve a right triangle and they don't kind of guide you into what to find first, what to find second, or what to find last. All right, so now I'm going to go back to XYZ and we're going to take a look at number 1. Okay. It says assume that alpha is opposite side A, beta is opposite side B, and gamma is opposite side C. If possible, solve each triangle for the unknown side, and we want to round to the nearest tenths. All right, so we're given that angle gamma is 43. We're given that side length A is 2.44. And we're also given that B is 3.07. right, so I'm going to sketch this out. All right, so this is 4.2 number 1. Given that gamma is 43, A is 2.44, B is 3.07. All right, so for standard labeling, we have alpha, beta, and gamma. So opposite angle alpha is side A, and that's 2.44. Opposite angle beta, we have side B, which is 3.07. And we're also given angle gamma, which is 43. So now if I go back to X, Y, Z for just a second, okay. And I stand corrected. Gamma is 44.3. All right, so let me just make sure I have the right dimensions. Out gamma is 44.3. A is 2.44. Okay, and B is 3.07. Okay. So now also notice that I'm given two options. I'm asked to find side C, and it's also giving me the option that a triangle is not possible. Now, the only way a triangle is not possible is if I'm given a side angle set of measurements, right? So here I'm given a side angle side, right? We're given a side, an angle measure, and a side length, right? So this triangle is possible. Okay. The only way you want to be mindful of that, if you're given a side angle, the dirty word spelled backwards, if you're given that set of dimensions, then you have to be careful on how you proceed. All right. So in this case, we're asked to find C, right? So if I take a look back at our formulas, right, this is the formula that we're going to use. Okay. So I'm actually just going to write that. So we're asked to find C. So C is equal to the square root of A squared plus B squared minus 2AB times the cosine of gamma. A is equal to 2.44. B is equal to 3.07, and gamma is equal to 44.3 degrees. All right, so we have C is equal to 2.44 squared plus B, which is 3.07 squared, minus 2 times A, which is 2.44, times B, which is 3.07, times the cosine of 44.3 degrees. All right, so we're going to put this into the calculator. Okay, and I have two instances of the calculator up. close one down. All right, so I'm going to put this into the calculator. So first off, let's make sure that we are in the right mode. I want to make sure that I am in degree mode, right? Because I'm given a degree measure. We're given 44.3 degrees. So I'm going to put this in the calculator as a square root of 2.44 squared plus 3.07 squared minus 2 times 2.44 times 3.07 times the cosine, right? So there's no need to put times. It understands that that's a multiplication. 44.3. I want to close off my argument for cosine. I want to close off my radical. And let me check what I have. 2.44 squared plus. Let me just put that in again. Square root of 2.44 squared plus 3.07 squared minus 2 times 2.44 times 3.07 times the cosine of 44.3. Close off my argument for cosine, close off my argument for the radical, and we get 2.15. All right, so I'll leave that on the screen for just 1 second. All right, and if we were to round to the nearest tenths, I believe we would have 2.2. All right, so we have 2.2 for number 1. All right, now we're going to take a look at number 2. So it says to use the law of cosines to solve for the missing angle of the oblique triangle. And here again, we're asked to round to the nearest tenth. So we're given that alpha is 41, B is 15, C is 33. All right, so I'm going to just sketch that out. All right, so this is 4.2, number 2. All right, so again, we have standard labeling, alpha, beta, and gamma. We're given that alpha is 41 degrees. We're given that B is 15. And we're given that C is 33. Right, so if I were to go back, let me just double check. Okay, alpha is 41, B is 15, C is 33. Here again, we're given 2 options. We're asked to find And I'm sorry, we're given A, B, and C. Yeah, my eyes are bad. We're given A, B, and C. All right, so A is 41. Let me change this. Okay, so A is 41. B is 15 and C is 33. We're asked to find alpha. All right. So we're going to use the formula for alpha. I guess before we use the formula, all right, let me just go back just to make sure. Okay, A is 41, B is 15. Okay, C is 33. And we're given two options, either to find angle alpha or if the triangle is not possible. So notice here I'm given three side lengths. I'm given a side set of measurements. I'm not given a side angle, so this triangle is possible. So now in order to find alpha, we were given a formula. We were given that alpha is equal to the arc cosine of a squared b squared plus c squared minus a squared over 2bc. All right, so going back to our formulas, right, we would use this formula. All right, since we're asked to find angle alpha, right, we're given three side lengths. So we're just going to substitute. We're going to substitute A for 41, B for 15, and C for 33. Right, so this is equal to the arc cosine of 15 squared plus 33 squared minus 41 squared divided by 2 times 15 times 33. All right. And we're going to put this into the calculator. And I have to flip the computer around. Well, no, I don't. Not really. Okay, I'm trying to turn on the calculator. Maybe I have to flip it around. Okay. All right, so I'm going to put this in carefully as the arc cosine. Well, first off, let's make sure I'm in degree mode. The arc cosine. And then I'm going to put a begin parenthesis for my numerator. So I'm going to put in a begin parenthesis for 15 squared plus 33 squared minus 41 squared. And then I want to close off my numerator. Next thing we're going to do is I'm going to hit a divided by, and I'm going to open up a set of parentheses for the denominator. And I'm going to put in 2 times 15 times 33. I'm going to close off the denominator. And I'm going to close off my arc cosine function. And now I'm going to hit enter. All right, so we get 111.8 degrees. Now you may have a different way of doing it. You can actually simplify the top, you can simplify the bottom, right? And then just divide by the arc cosine, or you can carefully enter everything in one step. All right, so no matter how you do it, you should have the final result of 111.8. All right, so I'll just bring that up again. All right, so we've taken a look at an oblique triangle in which you have to find a side length. We also took a look at an oblique triangle in which you had to find an angle measure. Okay, in the first instance, we were given a side angle side set of measurements. In the last instance, we were given a side set of measurements. All right. So now I'm actually gonna, before we get into the side angle case, I want to talk about Heron's formula. All right, and Heron's formula is used if you're given 3 side lengths and you're asked to find the area. It says if a triangle has sides of lengths A, B, and C, then the semi-perimeter is S is equal to 1/2 times A plus B plus C. And then you must use that semi-perimeter to find the area, which is follows. The area is equal to the square root of S times S minus A times S minus B times S minus C. Okay, all within the square root. Okay, so it's actually a two-step process. The first thing you have to do is find S. And then after you find S, you must take S and use that in the area formula. So let's take a look at an example. And I believe the very last problem deals with that. Okay. It says use Heron's formula to find the area of a triangle, and here we're asked to round to the nearest hundreds. We're given that A is 1.2, B is 1.7, and C is 2.7. All right, so I'm going to go back to OneNote and sketch that out. 1.2, 1.7, and 2.7. All right, so this is 4.3, number 12. Find the area. So this is A, this is B, and this is C, right? So A is 1.2, B is 1.7 and C is 2.7. All right, so the first thing we have to do is find the semi-perimeter, right? And that has a formula: S is equal to 1/2 times A plus B plus C. So we're going to substitute A for 1.2, B is 1.7, and C is 2.7. All right. So this is basically how we're going to calculate S. And I have to flip my screen around. Okay, and how do I make that go away? Okay, so let's calculate S. So that's 1.2 plus 1.7 plus 2.7, which is 5.6. We're going to divide that by 2. And we get 2.8. All right, so that's the first thing you want to do is find S. All right, and now we will find the area. So that formula is A is equal to the square root of S times S minus A times S minus B times S minus C. And we're going to substitute S for 2.8. A is 1.2. B is 1.7 and C is 2.7. All right, so that's 2.8 times, and I have to flip this around again. So that's S times S minus A. So S is 2.8. S would be, A is side length A, which is 1.2 times 2.8 minus 1.7 times 2.8 minus 2.7. And I'm going to put this in the calculator. So I have to be careful on putting this in the calculator. Right. I want to put in my square root, and I want to put in another begin set of parentheses. All right, you must always have an even set of parentheses. I'm going to put in 2.8 times 2.8 minus 1.2. I'm going to close that off. Times 2.8 minus 1.7. I'm going to close that off. I'm going to open up another set of parentheses, 2.8 minus 2.7. I'm going to close that off. I'm going to close off my square root. And we have an area of 0.70. And I'll give you just a second to write that down. So that's 0.70. All right, so now we taking a look at how to find a side length, given a side angle side set of measurements. We found out how to find an angle measure if you're given all three side lengths. We also found the area given three side lengths. Now we're going to take a look at the side angle side set of measurements. And I'm actually going to go back to the notes. Okay, I believe that's toward the end. And I was actually looking for the side angle. Okay. All right, so we're going to take a look at this one. Okay. Find, this is just an example. We're asked to find C. And we're given that beta is 48. We're given that A is 107. B is 45. All right, so I'm going to sketch this out. So this is alpha, beta, and gamma. So we have side A opposite alpha, we have side B opposite beta, and C opposite gamma. We're given that B is 48 degrees. We're given that side length A is 107, and we're given that side length B is 45. All right, so we're given a side angle set of measurements. So now this is the ambiguous case. We can either have a no triangle solution, a one triangle solution, or a two triangle solution. Now, this is the long part on this. Whenever you're given a side angle set of measurements, you should always treat the solutions as if you have a two triangle solution. All right, and this may be overkill for our actual problem. Hey, but this is how it's actually done. So you have triangle 1 and you have triangle 2. All right, so for triangle 1, I have alpha sub 1, beta sub 1, and gamma sub 1. And I also have side length A sub 1, B sub 1, and C sub 1. For triangle 2, we're going to have alpha sub 2, and the subscripts just represent the triangles. Beta sub 2, gamma sub 2, and then we have A2, B2, and C2. So for both triangle solutions, the given information goes in both. So beta is 48 degrees here. It's also 48 degrees here. Side length A is 107 in both triangles, and B is 45 in both triangles. Now, the reason you can have a no triangle solution, a one triangle solution, or a two triangle solution is that for a no triangle solution, the solution just doesn't exist. For a one triangle solution, that solution is an acute triangle. And I'll explain more about that in the next section, in our next class meeting. For triangle 2, your solutions can both be an acute triangle and an obtuse triangle. Okay. So here we're just going to take a look at a no triangle solution. And then I'll kind of get into details about the one triangle solution and the other triangle solution. But just based on what we do today, you should have enough information to just answer the two problems, number 10 and number 11. All right, so we have a side angle set of measurements. So we have to be careful. I'm going to put a little star by that. So that means we can have a no triangle solution, a one triangle solution, or a two triangle solution. All right. So the first thing we're going to do is, and if I were to go back to the suggested procedures, for given a side angle, which is case number 2, it says that we should find an angle using the law of sines. All right, so going back to our example, which angle could we possibly find? Well, we know angle beta, right? We know side length beta. We know side length A, so it's possible to find angle alpha, right, by using a law of sines proportion. So that's what I'm going to do here. I'm going to find alpha. But I'm not using the law of cosines, I'm using the law of sines. So the law of sines formula that I'm going to use is I'm going to take the sine of alpha divided by side length A, which is 107. I'm going to set that equal to the sine of 48 degrees divided by 45. Right? So I can get it all on one screen. So this is the law of sines proportion that I used. All right, so now I'm going to use a cross product property. Right, I'm going to cross multiply. So sine alpha times 45 is 45 times the sine of alpha. That's equal to 107 times the sine of 48 degrees. The next thing I'm going to do is divide both sides by 45. So we have the sine of alpha is equal to 107 times the sine of 48 degrees divided by 45. And now I'm going to take the arc sine of both sides. So alpha is equal to the arc sine of 107 times the sine of 48 degrees divided by 45. So I'm going to put this into the calculator. All right, so we're in degree mode. I'm going to put in the arc sine of 107 times the sine of 48 degrees. That should be a 48. The sine of 48 degrees. Be mindful to close off the argument for sine divided by 45. Close off the argument for arc sine, and I get an error. Okay. Now, when you get an error, I don't want you to think that it's something that you put in wrong in your calculator, although it could be. Okay, this would actually be a no triangle solution. So I want to just show something for just a second. Okay, so remember we talked about in an earlier section that the sine as well as the cosine value can exceed +1 and it can't be less than -1. So I'm actually going to take the innermost part of this and I'm going to simplify it. And I have to put the screen on to use the calculator. Okay, so I'm going to put in 107 times the sine of 48 degrees. Right, close off the argument for sine divided by 45. Right, and I get 1.76. We talked about the sine value can exceed 1 and it can't be less than -1. So notice that when we evaluate the innermost part of this arc sine, we get something greater than 1, right? Since we get something greater than 1, I'll just put that in this way, 1.76. Notice that we get an error. That alludes to the fact that this is a no triangle solution. All right, so we're going to just stop here with the no triangle solution. So just to recap, whenever you're given a side-side angle set of measurements, you should always treat the solution as a two-triangle solution. The dimensions you put in for triangle 1 are the exact same dimensions that you put in for triangle 2. Then we went back to triangle 1 and we were finding the angle measure using the law of sines, right? In this case, we were finding alpha, right? But when we went through the process and set up the law of sines functions, we found that the triangle does not exist. So when you're doing problem number 10, I don't want you to think you're putting something into your calculator wrong. All right, it's possible to have a no triangle solution. All right, so I'm going to stop at this point.